2000, and we're flattered and pleasured to introduce Mr. Ozan Sayman to insight us about the Plunger Lift Untapped potential. So, to give a little biography about Mr. Ozan, he's a co-founder of Plunger Dynamics and leads the development of software solution, data logging plunger, experimental and field plunger lift studies for operators. Mr. Ozan has conducted a PGL research programs, consulting projects, and developed mechanistic models from plunger lift, which includes fall and upstroke mechanics of the plunger and liquid unloading processes. He has published journal papers and made presentations at various conferences and workshops about plunger lift and plunger-assisted gas lift. In addition, Mr. Ozan is serving as a section officer of CPA Artificial Lift and Gas Well Delification Technical Section. Previously, he worked as an engineering consultant for a contractor of the ARPAE project and Chevron's R&D projects of aquatic downhole liquid delification tool. Mr. Ozan holds both a bachelor degree in mechanical engineering at Istanbul Technical University and a master degree in petroleum engineering at the University of Tuzla. Furthermore, if any of our participants has questions, they may ask them in the chat side and will later on forward them to Mr. Ozan. Without any further ado, Mr. Ozan, the stage is yours, and thank you so much.
Okay. Hello, everyone. This is Ozan Sayman. I want to talk about Plunger Lift today. Let me start with my agenda. So I'll start with the liquid loading. I'll describe what is liquid loading and which wells does it happen, and basically how to overcome which artificial lift methods are applicable for liquid loading. And then I'll go for the introduction of plunger lift. We'll talk about the plunger types and how those operation types works. And then we are going to go for plunger-assisted gas lift and gas-assisted plunger lift. We are going to talk briefly about the gas lift and operational boundaries of plungers in those systems. After that, I'm going to talk about our research work at the University of Tulsa. During my master thesis, I had continuous flow plunger lift research, and I'm going to talk about the physics about fall stage and upstroke stage of plungers. Then I'm going to talk about the field studies we recently made with our mechanistic models on plunger lift and other consulting projects. So let's talk about liquid loading. As reservoir pressure decline, your hydrocarbon production is going to decline. The gas velocity is going to be reduced in time, and your flow pattern is going to change from annular to charm flow and then slug flow, and you're going to see liquid loading. Let's describe the flow patterns with different videos. So in the left, you have annular flow. You can see this is a high gas velocity situation with 18.3 meter per second of superficial gas velocity. And in this case, you can see film is going up, and you can see in the core of the flow, the gas and some liquid droplets going up. In the next one, you can see a charm flow example. In this example, you can see the liquid film. Some parts of the liquid film is falling and some parts is going up. There's a stagnant liquid film, and this is called as charm flow. In a reduced superficial gas velocity of 1 meter per second, we are going to observe slug flow. This is shown in the right video. As you can see, slug's going to go up, but as slugs pass, then the liquid film is going to fall down. So as reservoir inflow decreases, the production eventually going to die because the liquid loading going to occur. So the flow pattern is going to change, and then you're going to see the slug flow, and the loading is going to kill the production. So what happens with the liquid loading? We don't want liquid loading because it creates hydrostatic back pressure to the well. So in this example, you can see this is the, let's say, the producing section, and this is the gas gradient above the liquid column. So in here, our pressure loss is smaller compared to the liquid loaded section. So with the liquid loaded section, we are going to have higher hydrostatic back pressure in the well, and we don't want that. So basically, liquid loading is happening due to insufficient gas velocity. The gas is not enough to basically have the liquid droplets going up. I have two videos in here. One is the annular flow video. You can see the film better in this high-speed video. You can see the film is going up in here, but in the charm flow, slug flow example, you can see the film, some parts of the film is actually falling down. So those two examples doesn't necessarily to be two different wells. This both flow pattern can happen in the same well. In the upper parts of the well, due to due to reduced pressure, gas is going to expand and the gas velocity is going to be higher. In the left plot, I have a gas velocity shown with the navy color. And I also have a critical gas velocity calculated with Turner correlation. This is shown with the red. As you can see in the top parts, we don't expect liquid loading to happen because our gas velocity is higher than the critical gas velocity. But in the bottom parts, this gas velocity declines. So instead of annular flow, you probably see in Charnow slug flow, and the liquid loading starts to occur in here. So how to avoid this? There's artificial lift methods. You can use different pumps, which can increase your basically reservoir inflow and the production rates, or you can try to reduce hydrostatic pressure. And plunger lift, gas lift, foam lift are good examples for that. So let's talk about where liquid loading happens. Liquid loading is known to be happening in the gas wells, but it's also happening in the unconventional place. So this is not related to just gas wells. There could be wells that producing high amount of oil and still having liquid loading issues. So I basically I did 3 different multi-phase flow simulation. This is a well schematic and fluid properties taken from Midland Basin. So basically for 3 different production rates, I plotted how critical gas velocity and actual gas velocity in the well shows. So the actual gas velocity is the dark blue one. As you can see at the 1.6 million cubic feet, you can see we don't expect liquid loading. However, as we go to lower production rates, you might be producing 400 barrels of water and oil and 1 million cubic feet of gas. As you can see, at some point, we are going to start to have liquid loading issue. As you go for the reduced gas production rates, you are going to have more and more liquid loading, more severe liquid loading cases. So in those cases, you either need some gas lift to increase the gas velocity, or you need to use plunger lift. So as you can see, this is not actually just for gas wells. It's also happening for the wells that's producing, let's say, more oil, more water than typical gas well. So let's look at some of the major artificial lift methods. So which is going to be a solution for liquid loading? So for fluid properties that happening in unconventional place and the gas wells, the PCP and jet pump is not the best options. And then again, for higher gas-liquid ratios, the gas lock can happen. And for deviated completions, you might not be able to use second rod pumps and ESPs. Moreover, some methods like foam lift and velocity strings only works for short periods. Foam lift is basically dependent on the chemical composition. So they are also not the best options for those wells that having liquid loading issue. So the plunger lift, gas lift, and the wellhead compression are the best options to tackle liquid loading problem. So plunger lift, we are going to focus on the plunger lift, and in the unconventional place, it typically started to deploy to use after 6 months. In some cases, they just start with the plunger and gas lift together from the day one. So with the plunger lift, you can increase your production rate. You can help to basically mitigate the paraffin issues, and you can cut lift expenditure. Instead of injecting more gas, you can inject less gas. Maybe you can remove the compressor. So it's a much more cost-effective method compared to others. So let's look at a typical gas production decline curve. So let's say this is a gas well and it's declining. This is the decline curve shown in here. With the liquid loading starts, we are going to see erratic production, and the average production per day is going to reduce, and you're not going to be able to continue with the gas well decline curve. However, if you install plunger here, you are going to tackle the liquid loading problem, and you are going to be able to have the similar decline curve with what you expected before the liquid loading stage. So between that is your cumulative production increase due to plunger lift. Okay, let's talk about how plunger lift works. What is plungers? So plunger is basically a metal cylinder. We are basically creating a sealing between the gas and liquid phases in the well. With this metal cylinder, we are just using the reservoir energy. So I'll start with the conventional plunger lift, which is a type of an intermittent production. So in this case, we are going to start with our well is shut in. So let's check the animation. Our well is shut in. There is no production right now. Plunger falls against static gas and liquid column. Pressure builds up because we shut our well in. And then as we open the production valve, the plunger is going to go up and it's going to remove that liquid loading happened in the bottom hole parts. So with that travel, with that cycle, we are going to be able to remove that liquid loading. So doing these cycles continuously helps us to basically get all those liquid loading parts, and our production doesn't die due to that. We are removing hydrostatic pressure with each plunger cycle. So basically, this is an intermittent production method. When we shut the well in, we build up pressure in the casing. When we open the production valve, we are unloading the liquid. This method is typically used for marginal wells when the reservoir pressure declines a lot, when you need to inject very high gas injection rates. Instead of that, you go for the conventional plunger lift, and then you're able to basically unload that liquid accumulated in the bottom hole. We have 4 stages in this. So when we shut the well, the plunger is going to fall and pressure is going to build up. As we open the production valve, the plunger upstroke happens. This is the upstroke stage. And then we are going to produce this liquid load. And at this stage, we are going to leave our plunger at the top in the lubricator. And this stage is called afterflow. So we let the well to produce by itself until the liquid loading starts again. So in the plunger lift area, there is the poor optimization techniques used. Most of the people using this use with the rules of thumbs. There's not too much physics they put in this plunger lift operations, which well to use, or plunger type selection. So we are trying to eliminate that with our research and other works with the plunger dynamics. So let's move on to continuous flow plunger lift. So continuous flow plunger lift is a different method. We don't need to shut the well in. So this method has little to no shut-in time. Shut-in times could be just 1 minute to just let the plunger fall from the lubricator. But in general, you can consider this like continuous production without any shut-in time. So in this case, we have 2 different continuous flow plunger lift types, bypass plunger and 2-piece plungers. So this is an example of 2-piece plunger. We have a sleeve. This is basically a metal cylinder, but hollow cylinder. The inside is empty. And this is a ball. So we let the ball fall first, and then we let the sleeve fall on top of it. When they merge together at the bottom hole, they're going to go up together and sweep the liquid. So this is my experimental facility from University of Tulsa. In here, we were able to have multiphase flow conditions. We have the liquid phase shown with the red dye color, and we also have the gas injection in this case. So let's start the video. In the start of the video, we are going to have the ball in the bottom part, and the sleeve is going to fall. You can see the churning flow. The sleeve is falling, and it merges with the ball and go up, sweep the liquid, basically reducing the hydrostatic pressure in the well. So this method is suitable for high production rates. It can go up to 600 barrels per day and 2 million cubic feet of gas. When it's used with the gas injection, this is called plunger assisted gas lift, PAGL. So we have only 2 stages in this case. We have only the fall and upstroke. In this case, we still have the lack of analytics happening for this. So the screening of which wells to use this method is not great. In terms of operational boundaries and plunger type selection, there is room to grow. And the operators always looking for optimizing the gas injection rates on those plunger assisted gas lift applications. Let's briefly go on the plunger lift types. So we define the plunger lift operation types as 2 types: continuous flow plunger lift and conventional plunger lift. So continuous flow plunger lift, you can apply before the liquid loading. It's suitable for higher production rates. And conventional plunger lift is for late life of the well when the reservoir pressure is marginalized. And it's suitable for lower production rate. Continuous flow is basically continuous production, but in the conventional plunger lift, it's an intermittent production type. You might be shutting your wells up to hours and then basically sending the plunger up and producing that liquid and having an afterflow time of, let's say, maybe 10 minutes or 20 minutes. Basically, this is an intermittent production. You are not going to have production on time all the day. So let's go on the characteristics. In the continuous flow plunger lift case, those plungers are able to fall much faster. They can even fall against the flow. However, in the conventional plunger lifts, the conventional plungers are not suitable to fall against flow, and they are slowing much slower compared to continuous flow plungers. There are 5 main types of plunger. We define this as bypass and two-piece plunger, which is continuous flow plungers, and also bar stock, pad, and brush plungers, which is suitable for conventional plunger lift. So let's compare the plunger fall stage for conventional and continuous flow plunger. So in the videos, this is a conventional plunger. Spiral plunger is falling against static gas, and then we have the same plunger falling against static gas with liquid film. This is a high-speed video. So this is the fall stage from our experiments, and this is how it falls against the liquid column. So conventional plungers is falling against basically static gas or static liquid column. In the liquid column, its fall velocity is reduced a lot more. And the continuous flow plunger basically fall against multiphase flow. In the right, you can see the multiphase flow environment. There's the two-phase flow here, and the sleeve, the hollow cylinder, is falling against the multiphase flow. Let's compare the upstroke stage. In the upstroke stage, continuous flow plunger lift relies on the gas and liquid flow. The gas and liquid flow itself creates a drag force, and the drag force basically carrying the plunger weight and the slug weight. So you can see the liquid slug is coming up. This is on top of the plunger. This is aerated liquid slug. And you are going to see the plunger next, how it sweeps the liquid from the tubing. So as plunger goes up, in this case, it accumulates the liquid slug on top of it. So we'll compare this with the conventional plunger now. The conventional plunger starts in the bottom, and all the liquid loading, all the liquid slug is accumulated on top of it, and it's going to start with that conditions. So the liquid slug is coming, and the conventional plunger is going to come. And it's going to have a liquid fallback. Some residual film is going to be left out after the plunger comes. So in the continuous flow plunger lift case, if you couple this with the gas lift, this is called plunger assisted gas lift, PAGL. And when the conventional plunger lift, if you are doing intermittent production, if you have a shut-in time, this is called gas assisted plunger lift, GAPL. Those terms are usually confused, but this is how we define that with the University of Tulsa. So let's talk about the gas lift methods, how gas lift works. So in a well, when we inject gas, we are going to reduce the liquid holdup. Reducing the liquid holdup helps us to reduce gravitational pressure loss. When we are injecting gas, we are also increasing the frictional pressure loss, and which also increase the compressor costs and emissions for our case. So in this visual, you can see we are injecting gas, and this shows this section has higher liquid holdup, but with injected gas, you are going to have less liquid holdup basically. And this is how it looks in terms of pressure gradient. So in the bottom parts, without the gas injection, the pressure gradient is higher. So this is going to increase the bottom hole pressure. However, when you inject gas, your gas, basically the pressure gradient is going to be less. So let's look at this on the nodal analysis. In the nodal analysis, we usually have inflow performance curve and the outflow performance curve. So we have an IPR in here. This is drawn like this. And what we try to have is a lower bottom hole pressure to increase our production rate. So in this case, there are different cases for the gas injection. So as you inject more and more gas, your gas to liquid ratio is going to increase. You can see this is the 300 of MCF per barrel GLR rate. And this is a higher bottom hole pressure. So in this case, we are going to produce less. But if we inject more, then we can lower the bottom hole pressure and we can increase our flow rate. But this doesn't mean highest gas injection is the answer every time. At some point, frictional pressure loss is going to be dominant. And as we inject more gas, we're going to see our bottom mole pressure is actually going to start to go up. So in this case, let's look at the gravitational pressure loss and frictional pressure loss in detail. So this is an outflow performance curve. This is shown with the red color. This is basically our bottom mole pressure with different gas flow rates. And I have the hydrostatic pressure loss shown with this green curve. And we also have the purple one for the frictional pressure loss. So as you can see, as we inject more and more gas, if our gas flow rate is higher, our gravitational pressure loss is going to be reduced. But in the same time, the frictional pressure losses is increasing. So what we want with the gas lift is, let's say we are starting from here, we want to reduce our bottom mole pressure and inject more gas. So you can see there is the optimum point where the pressure is at the bottom mole pressure is the lowest, which will increase the reservoir inflow and optimize our production rate. However, liquid loading can still happen in this case. This is for steady state simulation. So I also plot here how much gas flow rate we need to avoid liquid loading. So this is the Coleman with the Coleman critical rate, and this is with the Turner critical rate. Let's talk about the Turner one in this case. So if you don't want to have liquid loading, we would need to inject more and more gas to have this gas flow rate. As you can see, which is higher than this point B is higher than the point A in terms of pressure. So if we actually use plungers with the gas lift, we are able to go this point A. We are able to inject less gas because the plunger is going to avoid the liquid loading for us. So this is the advantage of plunger lift. It helps you to reduce the gas injection. You can even maybe remove the whole compressor. And basically, it helps you to avoid liquid loading and minimize the bottom mole pressure compared to gas lift. So let's visualize how it looks with just gas lift and with the plungers. In the left, you can think this as like a gas lifted well. This is a churning flow, and you are going to see how plunger is sweeping the liquid and helping to avoid liquid loading. Sleeve is going to fall, and it merges with the ball, and it goes up. As you can see, it basically reduces the hydrostatic back pressure for you and minimize your bottom mole pressure. Let's also talk about the intermittent gas lift and what happens with plunger and without plunger. So when your production rates declines, when your reservoir pressure declines, you can always have intermittent gas lift. So let's say your well is liquid loaded and you cannot produce anything. You can shut your well. You can build up pressure in the casing and try to shoot that liquid accumulate in the bottom hole with the casing pressure. So as you can see, when we try to do that without plunger, the gas is going to go from inside of the slug and it's going to escape, and we are going to lose most of the liquid. We are not going to be able to produce most of the liquid with intermittent gas lift. But with the same method, if you used plungers, if you put this metal cylinder as a ceiling, you are going to see most of the liquid is going to go up. So let me replay those things. In this case, you are losing most of the liquid with the intermittent gas lift without plunger. But in this case, with the plunger, you are basically producing most of the liquid. So let's go on the operational boundaries, when to start the different methods of the gas lift, plunger lift, in a typical decline curve I showed earlier. So we talked about how plunger lift helps to produce this amount when you avoid the liquid loading. So even before liquid loading, we can have maybe gas lift or just natural flow, but there would be stagnant film. There would be still higher hydrostatic pressure. And with gas lift and plunger lift, we can reduce that. So with the plunger lift, there is a case David Dahlgren showed in ALRDC workshop earlier. So before the liquid loading stage, he just applied those continuous flow plungers, and it showed the production is increasing up to 16%, and the liquid production is increasing up to 7%. So as we start to have liquid loading region, as we get in the liquid loading region, so there are the options to use. You can use intermittent production, you can use gas lift, but you would need to inject higher and higher gases, which means higher costs. So instead of that, you can use continuous flow plungers. With the continuous flow plungers, Polasek at 2013 in the Barnett, he showed that they were able to remove the compressor. They removed the gas lift altogether, and they just put continuous flow plungers. And their production is actually didn't decline any. It's actually increased marginally, but they were able to basically remove the compressor. This is a huge cost saving for them. And they were doing the hot oil treatment against paraffin deposition. With each plunger cycle, they no longer needed to use this hot oil treatment against paraffins or scale buildup. Another case is using the plunger with the gas lift. Maggie Burns from X2 Energy presented this paper to show plunger-assisted gas lift cases. So they have this well with the gas injection, continuous gas injection. But with the time, since the reservoir decline and the gas flow rate coming out from the reservoir declines, they needed to inject more and more gas. So they applied the plunger in it. They put continuous flow plungers in it, and they were able to reduce the gas injection up to 80%. And they also see the gas production increase. So removing compressor, easy to understand that you're going to cut in cost, but also reducing the gas injection can mean the same thing as well, because when you reduce the gas injection, if it's a well pad, then you can actually basically direct this gas to different wells where it's more feasible to use. Okay, so in the later stage of the well, when the reservoir pressure even declines more and more and the production becomes marginalized, you can use intermittent production or plunger lift. And this is one of the studies from EPA. They basically show the conventional plungers on average is increasing the gas production to 54%. It's basically reducing the emissions, and it helps to avoid chemical treatment. So to sum up the two methods, with continuous flow plunger lift, you can increase your production, and at the same time, you're able to cut costs. You can have lower lease operating expense. You can reduce the gas injection and chemical treatment. In the conventional plunger lift side, it helps to extend the life of the well. So the well production might be already dead because of the liquid loading, but if you put the conventional plunger, you're going to see substantial cumulative production increase. And it helps to postpone plug and abandon of a well. It helps to stabilize the production. It reduces the venting, reducing the emissions. So the whole plunger lift method is a low capital investment method. You can install with wireline installation. It costs less than, let's say, a gas lift or ESP or cycle rod pump investment. And the operating expense is also very low. This only uses the reservoir's own energy. You don't need to spend any gas to basically run a compressor or something. So it's going to use the well's own energy, and the operating expense is usually just changing some plungers. But you don't need to in most cases, you don't need to inject chemicals or hot oil treatments against scale buildup. So operating expense is minimized with the plunger lift. It's suitable for unconventional reservoirs, the gas wells, and there are many candidate wells. It's very popularly used in North American fields, and I believe there are more and more potential, but most of the operators around the world doesn't know how to use or which wells to use. So we are trying to help to basically understand where to use plunger lift. Okay, let's move to the research. I'll briefly summarize some of my work with the University of Tulsa. So in the University of Tulsa, we had two different experimental facilities. We had a static facility with 9 feet long, 2-inch ID pipe. We basically put different liquids in it. We injected air in it, and we had the proximity sensors, and we basically studied the plunger fall in this case. And then we go for the dynamic facility, where we were able to have multiphase flow conditions, and we had the test in that facility as well. So in the University of Tulsa, we had tests on continuous flow plungers, sleeves, balls, and bypass plungers. In the conventional plunger lift side, some of my colleagues worked on the pad, brush, bar stock plungers, and we also had in-house built smart plungers. So these are some of the videos from the static facility. You can see a sleeve falling against different flows, different liquids. We used water and different mineral oil with different viscosity and densities. But this is our dynamic facility. In the dynamic facility, we were able to use we were able to do conventional plunger lift experiments. We have a casing section here. We basically build up casing here. We basically build up pressure in the casing, and then we open the production valve, and we are shooting our plunger up with that casing pressure. And we can have various fall conditions to test conventional plunger lift. Same applies for continuous flow plunger lift. In the continuous flow plunger lift, we don't need to build up pressure in the casing. We are basically injecting gas and liquids continuously, and the plunger goes up with the drag, and it also falls against flow. We had different measurement methods here. We had pressure sensors, DP sensors. We were able to get a velocity profile with proximity sensors and optical sensors, and we were able to quantify liquid fallback with our quick closing valves, trapping the multiphase flow or trapping the fluid liquid falling back from the plungers. So let's look at the plunger fall velocity experimental results. In the left, you can see some of our plunger fall velocity results, but we have the sleeve results and ball results here in different mediums like water and different mineral oils. However, the fall velocity comparison is not applicable to field with just giving fall velocity out. We needed to get dimensionless parameters. So dimensional parameters helps us to characterize the fall mechanics. For every unique shape, every unique geometry, there is only one corresponding drag coefficient for each Reynolds number. In the right plot, you can see sphere, cylinder, and disc, and they have only one drag coefficient for given Reynolds number. So for each different shape, if you get the drag coefficient to Reynolds number relation, then you can apply this in the field because it's a dimensionless parameter. You can basically scale this up. So with this idea, we basically tested our plungers. We get the fall velocities. In here, you can see our force balance and how we get the drag coefficients out of that our fall velocity experiments. So we basically have a force balance here. At one point, we expect the plungers to reach the terminal velocity where they don't basically accelerate or decelerate. When they are in the same velocity at the terminal fall velocity, we are able to get the drag coefficient. You can see different sleeves and different balls and their drag coefficient. We were basically able to test in different fluids to have different Reynolds numbers, and then we were able to get this correlation out of this experiments. In the dynamic facility experiments, we furthermore investigated the multiphase flow influence on the fall velocity. So you can see these are the fall velocity results. With in the left, we have the same gas velocity of 6 meters per second, and the superficial liquid velocities of the different superficial liquid velocities of 0.01, 0.02, and 0.04 shown in this graph. With higher liquid injection, we expect the liquid velocity increase and the liquid holdup increase. As the liquid holdup and liquid velocity increase, the drag force is increasing and our fall velocity is actually reducing with higher liquid injection. In the right, we have the same liquid injection rate and we have different gas velocities. Normally, we would expect higher gas velocity result in slower fall velocity of the plunger. However, you can see the results are very similar. There's two effects of having high gas velocity for same liquid flow rate. When you increase your gas velocity, you are reducing your liquid holdup. When you reduce your liquid holdup, your mixture density is reducing, and this is reducing the drag force. However, when you increase your gas velocity, you're also increasing the drag force. So there's two effects seen here, kind of balancing each other out. In this case, when the liquid velocity is the same, but gas velocity is increasing. We also tested different plungers. These are some of the results from that. So for the basically same 9-inch sleeves, we had 1.9-inch OD sleeve and 1.88-inch OD sleeve. These tests are done in 2-inch pipe. So we were expecting to 1.88-inch OD sleeve to be falling faster. It falls faster, but it's only marginally fall faster. So there wasn't too much difference in the fall stage. And for the comparison of 9-inch sleeve versus 6-inch sleeve, we saw 9-inch sleeve falls faster than the 6-inch because of the higher weight. We were also able to test different deviation angles. In our static facility, we only see marginal drag coefficient change, but in the dynamic facility, we saw the multiphase influence on the fall velocity. you can see this is the vertical case and this is the 20-degree incline case. Let's move on to video's earlier stage. You can see the liquid holdup is higher in the plunger's traveling side. So this is basically reducing the plunger fall velocity. So basically, if you want to estimate the plunger's fall velocity, you need to be able to estimate the multiphase flow conditions in that part of the well. So we build up a fall model. We build up a mechanistic model. We used our reference drag coefficient to Reynolds number data from our experiments. We had corrections for wall effect, two-phase, and deviation. Basically, our model is doing iterative calculation to find the drag coefficient point for the given Reynolds number. And with this fall model, we just need the plunger's drag coefficient. For different shapes, this drag coefficient is going to change, but you can get this drag coefficient relation with experimental tests, or maybe you can have some field measurements with smart plungers. Perhaps you can use computational fluid dynamics for this, but you just need to get this dimensionless parameters of drag coefficient. After that, the fall model can apply every different parameter that happens in the well. You can use different fluid densities, different API, different specific gravity of the gas. Basically, you can use different plungers. If you know the density, weight of the plunger, or size of the plunger, you can basically apply that in the fall model. The tubing size, production rate, pressure, the deviation angle, it's all can be applied. We just need to have basically the reference drag coefficient to be able to estimate fall velocity with our mechanistic model. Let's move on to upstroke stage, how continuous flow plunger upstroke happens. So this is operated with little to no shut-in. You can see forces applying on a plunger in the right side. Basically, our plunger needs to carry its own weight, and it needs to carry the liquid slug on top of it. And the driving force of the plunger is the drag force because of the gas and liquid velocity. So in the conventional plunger lift side, you are building up pressure in the casing when you shut the well in, and its driving force is that casing pressure, difference between the line pressure. However, in the continuous flow plunger lift case, we are relying on the drag force. And for this time, we also use the drag coefficient. I denoted this as CD high, which means for merged two-piece plunger or closed bypass plunger for the upstroke. So before starting the experiments, the general idea about those continuous flow plungers, we weren't shutting the well in, but the idea was the plunger is going to go down, it's going to fall to the bottom of the assembly, and it's going to wait there to build up some pressure to be able to go up. But in our experiments, what we saw was instantaneous upstroke. So there was no wait time. It's going to go up immediately because of the drag force. So let's check the video in here. Our ball is sitting in the bumper spring, and the sleeve is going to fall from here. This is a video I took with my phone. You can see sleeve is merging here, and then immediately goes up. It's, of course, a slow motion video. So there is no pressure build-up time required for this case. So what we saw in the experiments was plungers was always surfacing without stalling. If it starts to go up, it'll go up all the way because pressure is getting reduced in the upper parts. The gas is going to expand more. And if it starts to go up at the bumper spring location, then it's going to up all the way. What we saw when it wasn't going up was for insufficient flow rates. If we reduce the gas flow rate lower and lower, we see no upstroke. And what we see is there is no pressure buildup when the plunger is sitting in the bottom hole. It just creates a marginal pressure increase at the casing due to the restriction. But you cannot send your plunger up without increasing the gas flow rate, or you just need to shut your well and build casing pressure to shoot your continuous flow plunger up in this case. So we also had a mechanistic model for upstroke stage. We basically coupled them together for plunger-assisted gas lift. We call them PAGL. So in the PAGL model, we have continuous flow plunger with hydrodynamics. So what we need first is the multiphase flow. We need to understand the multiphase flow in different parts of the tubing to be able to run our mechanistic models on plungers. So we need the plunger specs, the plunger's drag coefficient, In the fall stage, the model utilized that dimensionless parameters we got with our experiments. And in the upstroke, we use this drag-based method, and which is showing fair match in the field trials. We are able to estimate the plunger velocity and how much liquid slug we are going to remove from the well. And this model, basically, the mechanistic model, helps us to basically build the operational boundary for Pagel and for different plungers. So to explain on the flow pattern map, let's show like this. In the higher flow rates, in the right side, in the higher gas flow rates, you're going to have a boundary for fall. At higher gas flow rates, you're not going to be able to fall your, let's say, if this is a two-piece plunger, your tungsten ball is going to be the fastest falling ball, but at some point, it's not going to be able to fall. So the plunger is only applicable, the gas velocity, less than that operational boundary. And in the left side, we have a lower boundary. So this means this is the smallest gas flow rate required to shoot your plunger up. So between that, we can call this operational area. And then with our tools, we are also able to define the effective area. Where should you use the plunger lift? So with the mechanistic models, we got a fall model. We are doing multiphase flow simulation, which is highly influential on fall velocity. We are able to get the pressure and mixture velocity profile for the multiphase flow. Then we are able to run our plunger models. We have all the plunger types. We have all the different materials, different plunger heights and ODs. These are all applicable for different tubing sizes. And we are able to get accurate, our objective is getting accurate fall velocity. So one important thing is basically estimating the maximum flow rate for balls to fall against to understand when we can deploy plungers. Another thing could be avoiding early merging of ball and sleeve. In the video on the left, you can see ball is falling, but since sleeves are falling faster, it's going to catch the ball along the way. So it's catching the ball, and they're going to go up together. So we don't want that. We want ball to reach to bottom hole assembly, bumper spring, and then sleeve to merge with the ball at that location. Because if it's do a partial trip like this, we are not going to be able to remove the liquid loading in the bottom parts. So we want to avoid early merging. For that, we typically let ball fall and have an afterflow time. We are holding the sleeve at the lubricator to not have early merging like this. So we need to basically able to calculate how many minutes we need for this afterflow time to avoid early merging. Our fall model is able to do that. And it also helps for the cycle optimization for both shut-in and afterflow times. In the Pagel tool, basically we are doing continuous flow plungers with the gas lift. We have the multiphase flow simulation. With the plunger lift, we are able to get fall and upstroke velocity profiles, the hydrostatic removal estimation. What is important is we are able to basically optimize the bottom hole location. So when you're designing your well for plunger lift, you also need to design traveling distance of plunger, how much deeper you should go, and you can basically simulate different cases in our tool for different bottom hole location. And you can also simulate for different shut-in times, different afterflow times, basically optimize the plunger cycle. We are also offering nodal analysis and gas lift sensitivity capability with our tools. And our key deliverables becomes to optimize the gas injection, helping the plunger selection, and basically improving the production on time, and also avoiding operational problems. Talking about operational problems, let's go to some of our field studies. So this study, the operator reached us and they told us they are having a tubing deformation. So this operator has more than 100 wells with two-piece plungers, and they start to see some of wells starting to have tubing deformation. They actually tried to understand this problem, and they theorized there could be some other things related to buckling and perhaps water hammering. They tried to solve this problem with different methods, but they weren't able to solve it. And so they thought maybe it's related with the plungers. But not all the operators having this problem. So they were curious, like, what we are doing wrong. So they asked us to identify the root cause of the problem. And what we find was the plungers was falling with excessive fall velocity. So this operator was using surface compression. So their wellhead pressure was as low as 10, 20 PSIG. So in that lower pressure, the gas tends to become lower and lower. And they had high shut-in times. And against the shut-in, against the static gas, the plungers, especially two-piece plungers, can reach very excessive fall velocities. So what we saw was the wells, so they provide us 9 wells, 3 without deformation, 3 with mild deformation, and 3 with severe deformation. And we studied the plunger fall and upstroke velocities. And what we saw was in the fall stage, those wells with the severe deformation especially was having very high fall velocities. So in order to maintain the well integrity, we gave them a safe operation guideline, how many minutes they need to put the shut-in time or which plungers they need to use. So they were using 18-inch longer plungers, heavier plungers, which reach higher fall velocity. So they either need to reduce that. So maybe they need to use, instead of 18-inch plungers, maybe they need to use 6-inch plungers, or they need to reduce their shut-in because two-piece plungers are not designed to fall against the static gas. It's designed for the falling against flow. So this is another study from Johns Basin. So we are going to present this on the next Artificial Lift conference in August. So in that case, we were able to get the data, downhole pressure data, which is not always available with the plunger lift or unconventional place, let's say. So in the below plot, you can see the downhole sensor data with the navy color. So these are the bottom hole pressure with time. You can see this is like 1,000-day time frame, and close to the 200 days, they deployed the plunger in this well. So we did our simulations for this stage. So first, we tried to do the steady state simulation with Beck's and Brill pressure drop correlation. So when we do that, we are reaching this gray curve, which you can see is actually over-predicting the bottom hole pressure than the sensor data itself. So when we apply the Beck's and Brill simulation and then our Pagel tool, the Pagel tool is giving us how much plunger reducing the hydrostatic back pressure, how much plunger is basically producing with each liquid slug. And basically, we were able to simulate with the Beck's and Brill and then subtract the plunger's liquid unloading. And we reached this green points, the green curve. And this is this Pagel tool's bottom hole pressure estimation. So as you can see, it has a fair match. And we are going to talk more about the plunger fall and upstroke velocities and some optimization techniques and this presentation and the paper. So another study is from Midland Basin. So with a major operator, they asked us to develop a custom plunger lift software with well integrity alerts. And this is also helping them to understand operational boundaries, optimize the plunger lift operation. What we saw was the field data had shown a good match with our tool. You can see their high frequency data, how many cycles they're making here, and how many cycles we are predicting. And this is basically the runtime differences. So we were in, let's say, 11% error range for bypass and two-piece plungers given to us with this production rates. These are from the well test dates. So we are going to present this one in the next ATCE. In the same paper, we are going to also talk about some of our research programs with Chevron. So we had bypass plunger testing for different tubing sizes, 238s and 278s. And we tried different sleeves and different plungers. So you can see these are the videos from our experimental facilities. We also made a study on internally coated tubing. So they were asking if the coated tubing is going to be worn out with the plunger lift cycles. So we did 10,000 cycles and get the results of whether how much wear you should expect due to plungers. And this video is showing us as the bypass plunger. Normally, bypass plungers should fall with open clutch mechanism like this, but in some cases, we saw the plungers actually fall with the closed bypass. We were curious about if this happens due to hitting the liquid column in here. But what we saw was if you don't send the bypass plungers up into lubricator fast enough, it's not going to open this clutch mechanism with the rod. So we are also going to discuss all those things in this conference. So thank you for listening to me. If you have any questions, I would like to address them. Thank you for all the videos that University of Tulsa allowed me to use.
Thank you so much, Mr. Ozan, for the insightful and informative presentation. And thank you so much for the illustrative videos. Actually, it was great. And I want to thank you for accepting our invitation and giving us your valuable time for today. And we actually have a couple of questions that we want to ask you if you have any time. So our first question is, what are the typical challenges you have faced in a well with plunger lift systems?
Okay, so with the plunger lift systems, for us, we are mostly trying to optimize the wells, and we are trying to, if there's any operational problems, we need to identify them. So sometimes to use our tools, we need the multiphase flow simulation. For some operators, they want to use their own multiphase flow simulator, maybe third-party commercial ones. So sometimes those results are not, let's say, coming quite all right. So what we saw was, for a gas-lifted well, sometimes we get those multiphase flow simulation results, which is not in agreement with the casing pressure and analyst calculations. So this was a recent problem. So sometimes we need to tune our program for the given multiphase flow simulation commercial product. So this was one of our recent problems, let's say, challenge to overcome. And other than that, they're usually asking about the gas lift optimization. How can they optimize the gas lift? So basically, we are using our tool to optimize the plunger of cycles, and we are using both our multiphase flow simulations and the tool to optimize the well for them for different gas injection rates.
Thank you so much. So I actually have a question. What kind of mechanical manufacture do you actually face during the intermittent production, like mechanical manufacturing or any mechanical problem?
Mechanical problems, I mean, if you have a high fall velocities, you can always damage your bumper spring and bottom hole location. If you send your plunger up too fast, you are going to damage your lubricator at top. Those are the problems, and our tools always giving well integrity alerts if the tool is estimating too high fall velocity or upstroke velocities. And with time, also, if you asked about the mechanical things, the plungers itself is going to worn out, and you need to going to change the plunger. The time for the changing might be between, let's say, a month, maybe up to 6 months. Those seems to be the challenge that's coming to my mind.
Thank you so much. So our third question is there any limitation for plunger lift system if there's sand production in the well?
Yeah, plungers are used with sand production. There are different types of plungers. So it's also related with your, basically, how you want to mitigate your sand production. Some operators might want to produce that sand, some might not want to produce it. So there are different plunger types that helps with the sand. And let's say I showed the bypass plunger video, which might not be great for sand production. So if there is issues like that, we are also considering that. For some wells, the brush plungers are better, but for some wells, maybe use spiral plungers. It's up to your also the sand production and if you expect scale deposition or not.
Thank you so much, Mr. Ozan. So no more questions have been forwarded to our chat side. So thank you so much again for accepting our invitation and giving us your valuable time. It was actually a very illustrative presentation. And thank you again. And we wish you a very good day. Thank you. Thank you so much, Mr. Ozan.
Have a nice day.
Have a nice day.